Okay. So when we have this problem, we have many potential inputs that I can have to predict this variable. The first thing that I could do is to put all the variables and try to predict. Sure, it's a no-brainer, but it's a sort of waste of time. Because if this number is very high, like 50, okay, you might run into the trouble of overfitting. So we need to reduce this number to the smallest possible. So for that, we need to do first an evaluation of these inputs. The first assessment that I need to do is what is called is cross correlation. Who have heard about this term? What is cross correlation? Cross correlation means that I'm going to evaluate the correlation between every variable against each other. Why? What I want to find if they are correlated.
It could be influencing each other. Your x's could be influencing each other. So kind of tease that out.
Yes, that's the concept here. We want to find which Fa is correlated to Xm. So why? Because if they are highly correlated, let's say the correlation of them is 0.9 or 1, extremely high, then I don't need one of them. I can discard one of them because they're giving me the same type of information. It's like doing a correlation between two vegetation indexes that, let's say, the maximum describe healthy vegetation, the value of 0 describe water. So like an NDVI and another index, but it's giving me just the same range of values. So what I want is to find this highly correlated, so I can eliminate it. So I can discard it. So my initial 50 becomes 50 minus these highly correlated inputs. So this is the first step. So let's see what I did in the model. In the model we have, and if you want to run this code, run in the terminal command, the pip install mx mlxtent, copy, paste. So let's run it. So we're going to import the file with all the spectral bands. Thermal band is band 6, and all the vegetation indexes in that file, the 50 vegetation indexes. The last column is soil moisture. So first, I am going to, here in the second cell, I'm going to eliminate the column crop because it's a text, it's alfalfa, corn, or barley. I am going to also eliminate the, or no, I'm going to transform the temperature column, the surface temperature band 6. I'm going to divide it by the temperature of water at 0 degrees Celsius. Why I do this transformation? Because all the reflectance values are from 0 to 1. All the vegetation indexes are going to be in a scale from 0 to 1, but temperature is in kelvins, so it's in the 300s. When you build a regression model, you try that the range of the values of every potential input are similar. So if you have one that has a scale of 10,000 versus 0 to 1, the variable with the larger scale becomes predominant in your model. So if you scale it down by an artifact, in this case, the division by the Kelvin temperature of frozen water, then it becomes a more similar, the behavior of the data never changes. What it changes is the magnitude. So now I have all my table ready. So what I'm going to do here in the next part is I'm going to run on the table a correlation between all the variables against everybody. So it's a very large matrix, and I'm running it in absolute terms because I can have positive or negative correlation. So by making it absolute, I can have values. For example, the correlation of band 1 against band 1 has to be 1. It's a perfect correlation. Correlation band 2 and band 1, look, 0.99. They are highly correlated. Band 3 and band 1, 0.98. So in statistical terms, it doesn't matter which band I choose. I can choose only band 1 and discard the other 2 because the information is very similar. So this is the coefficient correlation. So this is soil moisture against band 1 and this vegetation index against band 1. Some correlation have a higher, some vegetation has a higher correlation, others have lower. So we're looking to identify these ones. They have high correlation. So we can toss out some of them. Now, once we do that, because this is a table, the initial table is a correlation of everybody against everybody. Basically, if we look at the diagonal on the top, it's always 1. Band 1 against band 1, 1. Band 2 against band 2, 1. Band 5 against band 5, 1. So I have this diagonal of ones because they are comparing to itself. So what I want to do in the next step is I want to toss out or eliminate all the values that are below the diagonal because it's just a mirror. And I do that in the next step. It's a quite a complex formula, but you can see now that band 5 and band 5, I toss it away, but everything that was below the diagonal also is not a value. I do this to have just only unique values between the correlations. Now, here is the decision I need to make. Okay. In this new matrix that I have, I need to put a constraint. What is the the minimum level of correlation between two variables at which I decide they are highly correlated or not? So perfect correlation is 1. Less correlation is 0.99. Lesser correlation is 0.98. But at which point I say if the correlation is equal to or higher than this value, these two variables are highly correlated. So that will depend on you, but the higher the value, the less chance you have to throw an important variable, but also if you keep that value too high, like 0.99, the chances are high that you will keep a highly correlated variable. So in this case, after thinking about this, I think, well, I'm going to choose 0.95 as my threshold. Not too low, not too high, but I could have chosen 0.9, and that decision would have been okay. So, yeah.
So band 2 and band 1 have like a 0.99.
Yes.
Chooses band 1 or band 2?
It's going to choose, in this case, it chose to discard band 1.
That's by design?
By design. So it was, if we keep 1, if we keep 2, the band 1 is already represented by the band 2 because of the high correlation. But band 3 and band 2, the correlation is lower than 0.95. So both of them are kept in the system.
Oh, okay.
Okay. So the correlation is yes.
Okay.
So in this is the ones that are left. So we have in Landsat, this is Landsat 7. So we have blue, green, red, near infrared, shortwave 1, temperature, shortwave 2. There are 7 bands. So it dropped the blue, is keeping the green, is keeping the red. Let me see. Yep, it's just, oh, no, sorry, it is the opposite. These are the bands that are going to be tossed away. Is what is going to keep are going to be here. Is keeping band 1. Band 2 is highly correlated to band 1 and is discarded. Band 3 and band 2 seems to have a good high correlation with band 1, so it's keeping band 1.
Oh, okay. It's like treeing it.
Huh?
It like kind of trees it down.
Yes.
Okay.
So then, but band 4 has very low correlation against any other band, so it's kept. Band 5 is kept. The temperature is kept. Band 7, which is the shortwave 2, is discarded. But after that, it comes soil vegetation indexes, and even the soil moisture is kept. So we have about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we went from 50 to 17. That's the variables that my approach to drop that to get the smallest possible potential variables as taking. So now I have 17. Going back to the initial question, do I need all the 17 variables to predict soil moisture? Or could I find a smaller number of predictors or vegetation indexes to predict soil moisture? So could I reduce this? I did my statistics, and this is how far the statistic can take me. Okay, so let's do that DAM approach. Let's use those 17 to predict soil moisture. I need to run everything on top. Okay, so using those 17 variables, no, sorry. Using one variable, here I'm using this vegetation index, I get a bad correlation. If I try to get root mean square error and the coefficient of determination, this value is already too high of an error. It's saying that for any soil moisture value, I have a plus minus 0.14. This is huge. This is huge. The value that I'm looking, it should be around, but this is too high. The R square is showing us very poor correlation. Now, which of those variables can predict soil moisture? So in the next cell, we're going to iterate one by one of all those 7 things to see if I get a better statistics than using one vegetation index or the one that we chose. And here they are. Vertical axis soil moisture, and you have band 1, band 4, band 5, band 6. There is no correlation there. At least I don't see it. Okay, so none of those 7 things alone can predict soil moisture. Okay, so now I have to face that question that I'm trying to avoid. How many combination of bands, or what's a subset of those 7 things I can use to predict soil moisture? So we're going to use a concept here, call it stepwise regression. Have you heard about this term, stepwise regression? It's a very powerful tool. If you can manage that, you can avoid in many opportunities the use of machine learning, because the concept is very simple, but it's very powerful to find a set of predictors that can do a complex job. So a stepwise regression, let's imagine we have y in function of xn, x1 to x17. But we want a subset. Now, it might be that the best subset might be a combination of 2, combination of 3, combination of 4, or combination of 17. We don't know. We tried combination of 1 and we didn't find anything. So we need to try combination of 2, 3, 4. So there are 3 ways to solve this, to get the best subset. The first one is what is called the forward variable selection, FVS. What does it mean, the forward variable selection? I am going to iterate. I'm going to iteration or x from 1 to 17, do a linear regression as B, calculate, let's say, R square, okay, and give me R square 1, R square 1 to r squared 17. Okay, it's doing a linear regression and calculating the coefficient of determination of that linear regression. From here, pick the best. Let's imagine is r squared 5. Okay, that means x5 is kind of the best index. Now, x5, now I'm going to do this loop again, but I'm going to say the equation is going to change. Now it's going to say x5 plus b. So because in the first run, I found that x5 was the best, I'm going to keep it. And now I'm going to do combination of two variables, but including always 5. So I have this new equation. I'm going to calculate a new r squared, and I'm going to have now from r squared 1 to r squared 16, because there is one less variable. And from here, I pick the best again. So it might be that the best is x2, x5. I do a next loop. A, x, x2, x5 plus b. So every time I iterate, I'm adding the best of the previous iteration. So what I'm building is a sequence of predictors. Let's say iteration 1, 2, 3, 4, or let's call it variables. And here is the r squared. What's going to happen is when you do the first iteration, the r squared is here. You add the second, is here. You add the third, is here. You add the fourth, is here. You add the fifth, it doesn't change. You add the sixth, it start declining. You add the seventh, keeps declining. What is this is telling us is there is a best combination of 4 that can give us the best r squared out of those 17. So what this loop is doing is iterates a single variable, keeps the best. Now iterates combination of 2, keeping the best from the previous one, and calculate the best, and so on, until we got, let's say, x5, x2, x10, x11. And so my recommendation here as an equation is going to be from this method, the forward variable selection recommendation is going to be y is in function of x2, x5, x10, x11 plus b. So this should be A. I got an equation. Now, this is the forward variable selection. There is the opposite. The opposite is the backward variable selection. You start with all of them, okay? And then you eliminate one and keep the best of those 15 iterations, of the 15 variables iteration. Then you keep the best correlate the best r squared from those 15, and then you start eliminating another and another. So instead of doing it this way, you are doing it this way. And the thing is, this is the backward variable selection. And here is the trick, that these two rarely agree. If you do it one that moving forward and the other doing backward, this might be x17, x12, x2, x5 plus b. This equation can be completely different than this one. What is telling us that there are multiple solutions or multiple combination of inputs that can solve the same problem. So we need to implement this. If we try to do it from scratch, this variable selection, which I was naive in my PhD and I was